Yo, what's up? Let's do some leak code, get some gains in the brains. Number of beautiful partition. Yeah, so this one took a while. I finally managed to get it. How do you do it? Okay, first let's read the question. You are given a string S that consists of the digits 1 to 9 and 2 integers k and min length. A partition S is called beautiful if the string S can be partitioned into k non-intersecting substrings. So no letters can be left out. No chars can be left out. It has to be completely split. You have to find exactly k minus 1 split points. But you can only split it such that each substring that is made starts with a prime and ends with a non-prime. And because chars only go from 1 to 9, then the only primes there are 2, 3, 5, 7. So I was to start with a 2, 3, 5, 7. Our goal is to find how many possible ways to partition the string such that each substring has at least min length and the string has to be partitioned into k. So let's look at this one for example. One good starting point is just figure out where exactly are the primes that follow a non-prime. The 3 here is a prime, but it doesn't follow a non-prime, so that doesn't count. 5 is a prime, doesn't follow a non-prime. 2 is the first prime here that follows a non-prime. So 4 is the non-prime, 2 is the prime. So let me just mark down the index there. So 4. And then we have 5 is the next prime that follows a non-prime, so that's 1 there. And also 3, so there. Let's fill the rest with... This can be 0 because the first one is a prime, but it doesn't follow anything, so that's a special case. Let's fill the rest here with 4, so that I know when in any position here, if I query a position here, I can know from this position what is the first prime that follows a non-prime to the left of this position. Then I know immediately. I don't have to go to search for it. First prime following non-prime less than or equal to I, with index less than or equal to I. That will be helpful. Yeah, so this question is a combinatorics question, and that usually means DP. It's a very DP-like question, so let's just try DP. DPs always have a subproblem. So what is the subproblem? Okay, well, how many dimensions would this DP be? Everything is capped by 1,000, so we know we can do n squared. N squared will be fast enough. So let's just assume it's n squared. We can say k and I. So k is the number of substrings that we have to make, and I is the position in the string. So what would this be? Or if you just make it equal to the answer, the number of ways to partition S into k substrings. Number of ways to partition substring 0 to I into k substrings, into k beautiful substrings. If we had that, is it possible to figure out the transition of this problem? We know where the first prime following a non-prime to the left of my current position. So if my current position here is 10, so the value at 10 is 1. The first prime following a non-prime to the left of me is 3. How do I know that? If, say for example, the min length is equal to 3, I can't choose this 3 here, because if I partition here, I can only make a length 2 substring. I would have to look back at least 2 places. If this was the prime and this is a prime, if this was the prime, 1 is not a prime, then I can make a string of min length 3. So I have to look back min length minus 1 places and then check, what's the prime to the left of this position? Well, it's 7, so 7 is this index. 7 here is 5. I can make a partition here, 5, 1, 3, 1, and that will make a partition there. Assuming that I've made this a substring, well, I can take this string here and ask myself, all right, so what's the answer for this substring, and just add that to my answer for dpki, right? So what's that? that's dp. First of all, the first prime to my left, so the previous time pp. Alright, what is pp? pp is equal to, okay, let's make this array called pp, and let's make this one called ppi. So we can say ppi is equal to, what did we say? We said I minus min length. That's going a bit too far to the left, so let's add one. If our min length is 3, we want to go 2 places down, so 1, 2. So that will give us, in this case, 8. Now position 8 of the pp will give us 7. So using this to index into the ppi. Now ppi is the position of the prime, so in this case 5, but I actually want the position of this 8 because I want to find the answer at 8. So I could just do ppi minus 1, and I'm writing this in the wrong place. It should be the second index into this dp. The k is k minus 1 because if I can make k minus 1 of this substring, then just adding this one will make it k in total substrings. So I know this will be in my answer somewhere. And then I add another dp. Okay, try to figure out what that is. So this dp here handles the case where I can find out the total number of ways to split this substring and adding this substring to it to make a total of k substrings. But what about any substrings that cross between this substring to this substring? So say for example, this 2 here, there's a substring that goes across this partition all the way to the end. That isn't accounted for if this is a possible case. So how do we deal with that by leveraging another dp? Well, I would recommend that we actually use the same layer k, because let's say we choose another element before our current position I. So our I is currently at the end, right? If we choose any element before this and get the dp value of that at k, so that means, say for example, arbitrarily I choose this substring here, and I know how many ways I can partition this substring into k substrings. Well, it doesn't matter where, but the last partition of this substring, the last partition of this substring starts with a prime. Why don't I just extend that substring all the way to the end, and then that's the same, right? So that would work. So adding this value seems like the right move to do. Now this is kind of a tricky part. Which element do we choose in this layer dpk to add to this transition? Well, let's just consider ppi for now. Alright, so if we choose ppi, that means, let's say this substring here. Now this substring here would give us the number of ways we can partition this part into k substrings, and then whatever prime we have at the end, we can extend it, that substring to the end. That might not cover all cases. Why? Because we have to consider min length. Actually, let's consider this substring here, and let's say for argument's sake our min length is 4. We'll consider all possible ways we can split this up into k substrings of min length of each, where each substring is of length 4. That doesn't count for the case where I can do 218 all the way down to the end here, right? Why? Because 218 is a substring of length 3. So if I just do total number of ways to split this substring into k pieces of min length 4, I'll miss this case here, 218 to the end. Because 218 is not long enough to be a substring here. So I missed that case. Choosing the ppi minus 1 would not work. So does it work if I just choose maybe the I minus 1? Alright, that's tempting to do now that we've seen that case that we missed. But this actually might be overcounting now. Why is it overcounting? Well, we've already considered the case here from 2354218, and we are already taking this as a substring, or 5131 in this case here. So keeping that in mind, we don't want to repeat any cases that involve partitioning this last piece here. in this one here, otherwise that will be overcounting. Okay, so let's say we take I minus 1 for example. This is I minus 1. Number of ways to partition this substring into k pieces will include 513 as a substring. And then by what we're doing, we're extending this last substring to the end. That's this case here, 5131, which we already counted in this part of the DP. So we don't want to redo that case. So definitely I minus 1 won't work here. We want to consider at that prime only up to that prime PPI plus min length minus 2. And bear with me here. So if min length is 3, then that means we're at position 7 here, which is 5, and we add 1 because it's 3 minus 2, so that's at most up to this position here. Now we can use the DP at this position here, split this, that is, we can use the number of ways you can split this substring into k pieces and extend whatever the last substring is to the end. Because we know that because the min length is 3, there is no way that this last substring can start at 5. It has to start at 8 or some number less than 8. So this is best position to use. Probably have no edge case. We don't want this value at here to ever go beyond I minus 1. So let's just make sure that we take the min of this and I minus 1. And what's the base case? Alright, so we could probably just do, well, if it's 0 indexed, let k equal to 0 mean we're actually partitioning the substring into one substring, which just means making no partitions. So actually 0, let's redefine k to be the number of cut points. So if there's 0 cut points, we're just using the whole string. Then the base case would just be for this, it would just be 1 for the whole thing, except if I is less than min length minus 1, then it's not possible to make a beautiful substring, so that's just going to be that. Now the base cases are handled, the next case can leverage off the base case, and in the end we can find the answer, and the answer is going to be k minus 1, the number and the size, the number of characters in S, call that n minus 1. Okay, so all that's left to do is to code that out.
Alright, let's code this out. First thing is, what happens if the string starts with a non-prime? Then it's definitely not possible. Answer is 0. It's not possible to make a beautiful substring out of this, or any substring out of this. Yeah, the first one has to be a prime, the last one has to be a non-prime. If the first one is not a prime, or the last one is a prime, n is equal to s dot size n minus 1, turn 0. Another edge case is if k is equal to 1, so only make one substring out of this whole string. That's just taking the whole thing. We know that that whole substring can be beautiful because we had that check before, so just return 1. Okay, now let's make this pp array and initialize a dp array as well. So let's make this pp here. This pp is just the first prime following the non-prime with index less than or equal to I. Okay, this probably makes more sense. Closest prime following non-prime with index less than or equal to I. Now if s at I is a prime and the previous one is not a prime, I want to make pp at I equal to I. Otherwise, pp I should just be equal to the previous one. Now for the actual dp, for int I is equal to 0. Actually, I just realized something. ppi is always less than or equal to I minus min length plus 1. Assuming that it's equal in the worst case, then we have I minus min length plus 1, and then here we add min length minus 2 to that. The min length has opposite signs that cancels out, and then we have I plus 1 minus 2 is just I minus 1. So we actually don't need to do this min thing here. So let's go through all k values which start at 1, because actually we should initialize the DP first. I want DP at 0, 0 cuts in the string at I to be equal to, if I is less than min length minus 1, then it should be 0, otherwise 1. Why? Because we know that a string that ends at position, starting from the start and ending at position min length minus 1 is of min length. Anything below that would mean it's not possible to make a substring of min length. Int I is equal to 1, k less than capital K plus k. Let's go through each I value. And do we want to start I? Where do we want to start I from? We know it's going to be 0 for any value less than min length. So we actually want to start at min length. Okay, then let's find out what PPI is. PPI is equal to the PP of I minus min length plus 1. I'm just following the formula. One little edge case is PPI could be 0. So doing PPI minus 1 not work. In fact, if we do, we could just say if PPI is less than min length, continue. Oh, and we should return something. All right. See if that works. All right. Hope that helped. If that did, give a like and subscribe, and I'll see you in the next video.